Alrighty, good morning, Algebra 2 CP. This is Thursday, April 16th. I'm trying to go to a full screen preview, and for whatever, there we go. There we go, perfect. Thursday, April 16th. Hopefully you all had a fantastic Wednesday and start to your morning this morning on Thursday. Today, we are starting a brandy new topic today on graphing rational functions. It is rational functions being the entirety of quarter 4 for Algebra 2. We're going to start with graphing, we'll move into solving, and then we'll cover some word problems later in the quarter. But this is it. We are in, I don't want to say we're in the home stretch because we still got a whole quarter in front of us, but we are approaching the last couple topics for Algebra 2 CP, which is bittersweet. I think it's exciting, but at the same time, it's like, oh man, our time has almost come to an end. But let's savor the amount of time that we have left, shall we? One thing that I usually do to start out the rational functions unit is, first of all, define what a rational function is. And second of all, I ask students to take a couple minutes to fill in this table of values here for the function 1 over x. Okay? One thing that I want to do right out of the gate is, like I said, define what a rational function is. So just very quickly, I want to note for you that a rational function when you say the word rational function, that means it's any function that has a variable in its denominator. Oh yeah. So now we're going to be looking at some essentially fractional functions where we see this value in the denominator containing a variable, right? Just like how we did radical functions, where values in the variables could appear under the square root or cube root. With rational functions, variables appear in the denominator of fraction. And that leads to some interesting results. So if I'm trying to fill in this table of values, right, this is just for the function 1 over x. Not surprisingly, when we deal with rational functions, we do start by talking about what the parent function is, just like we did with radicals. If you recall, the parent function refers to the most basic function of a particular type. And it's useful to start by talking about the parent function because the parent function, like everything, is a manipulation of the parent function. Everything follows those basic rules and ideas that the parent function sets forth. Okay? So our parent function with rational functions is f of x is equal to 1 over x. That's the most basic way that you could have a function that has a variable in the denominator. It's not 2 over x, it's not 3 over x, it's not 1 over x plus 5, it's not a number on the outside, it's nothing else crazy, it's just 1 divided by x. That's the most basic way we could have an x in the denominator. Okay? So, going from there, again, what I usually ask students to do, as I do now to get started with this, is to complete this table of values over here by taking these numbers and plugging them in here. I know that's tougher to do virtually, so I will walk you through it a little bit step by step here. If I take this value of -4 and plug it into 1 over x, that's going to be 1 divided by -4, hopefully you can see that that's going to come out to be -1/4, right? Because 1 divided by -4 is -0.25, so -1/4, yes? If I'm going to sketch a graph of these points, take a look at how it's going to look. All right. So I start with a point at -4, 2, 3, 4, comma -1/4. It's like really, really close to that x-axis, but not quite touching it. See that? Our next point, if I asked you to plug in -2 into the function, hopefully you'll see that you would get -1 over 2 or -1/2. So another point on this graph would be at -2 comma -1/2, like that. If I asked you to plug in -1, you would get 1 divided by -1, which is -1, right? So I'd have a point at -1, -1. Now going into these fractions, do not freak out when you see 1 divided by a fraction. In order to divide by a fraction, we don't panic, we don't cry, we don't give up, we multiply by the reciprocal. So something like 1 divided by -1/2, I'll just write it out. Where should I write it out? I guess I'll write it out down here. If I have 1 divided by -1/2, to divide by a fraction, we multiply by the reciprocal. That's going to be the same as 1 times -2 over 1, which is -2. Okay, so just keep that in mind, that when you divide by a fraction, it's the same as multiplying by the reciprocal. This is now -2, meaning I have a point at -1/2 comma -2. And if I plug in -1/4, hopefully you'll see the same pattern, that if I do 1 divided by -1/4, that's going to be 1 times the reciprocal, right? Divide by a fraction, multiply by the reciprocal, -4/1, which is -4, like that. Which is -1/4 comma -4, just about like here. Okay? And you should see that this little section of the graph ends up looking kind of like this. Right? Do you see that? It's like this connected line, or curve rather, that kind of looks like this. Yes? Let's skip over 0 for now, and let's proceed in the positive direction. What if I start here and go backwards? So how about 4? If I plug 4 into there, hopefully you'd see it's really going to just mirror the negative side, where you're going to get something like 4 comma 1/4, 2 comma 1/2, right about there, 1 comma 1, because 1 divided by 1 is 1, 1/2 comma 2, and 1/4 comma 4. So now the question is, the million-dollar question is, what happens at 0, right? What's the deal? If I do 1 divided by 0, what do I get for an answer? Well, that's the trick question of all trick questions in math. You cannot divide by 0, and maybe you remember that as being one of the cardinal rules of math. Like, you can't square root a negative number, because otherwise you have to delve into i's, and you can't divide by 0. 1 divided by 0 is undefined. Okay, it's undefined. So what does that mean? Does that mean that we connect these two things kind of like this? Does that mean we put an open circle at 0? What does this graph look like? Well, it actually kind of looks like two sections. One section kind of like this, which, by the way, both of these approach the axes but never actually touch them. And one section like this that approaches the axes and never actually touches it. Okay? Does everybody see that idea of how we got that with all those points? This concept, by the way, of approaching the axes but never actually touching them. See how we'd always get closer and closer and closer. We can't plug in 0, but say I plug in like 1/8. Well, if I plug in 1/8, 1 divided by 1/8 is 8. So you're going to get a point at 1/8 comma 8. If I plug in 1 over 16, it's going to be 1/16, a little teeny tiny fraction on the x-axis, comma 16. And then what if I plug in 100? Well, you're going to 1 over 100. You'll get 1 over 100, little teeny tiny fraction, is going to shoot way up to 100. So this is going to accelerate forever, all the way up and up and up and up and up, but it is never going to touch that y-axis. Likewise, yes, 0 is always undefined. I'll get to actually how to graph in general, Luke, in just a little bit. But that's the idea, is that this value is undefined. You cannot divide by 0. Okay? This division by 0 and this idea of approaching a value forever and never touching it is what's referred to as, and yes, this is a real word, it's what's referred to as an asymptote. Okay? An asymptote. You gotta say it almost like a cowboy spitting in a bucket. You gotta say like an asymptote, like a spittoon, right? An asymptote. So an asymptote is essentially this line. It doesn't have to be a line, but for our purposes in Algebra 2 CP, it will be a linear function. It will be a straight line, but it is a linear function for our purposes in Algebra 2 CP. I'm going to put linear in parentheses because it doesn't necessarily have to be. You can get higher up in math and deal with parabolic asymptotes. We're not going to go there, but they do exist. That another function will always approach but never equal. Okay? It's a function that another function will always approach but never equal. Here, you can see that we have an asymptote on the y-axis because the function always approaches this y-axis but will never actually equal it because we can't actually plug in 0, so I can't actually get a point that exists on the y-axis. Likewise, you may notice that we also have an asymptote on the x-axis because I can never actually get 0 for my solution, right? You could get numbers that get really close to 0 as you continue plugging in bigger and bigger numbers. Think of if you did 1 divided by 10. Well, that's 1/10. If you plugged in 100, that would be 1 divided by 100, which is 1/100th, really, really tiny. If you plug in 1,000, that's going to be 1 divided by 1,000. But you will never actually hit the y value of 0. What value could you actually plug in that would result in an answer of 0? There isn't one, right? So that's why we have these things called asymptotes. Now, there are two types of asymptotes, as you might have guessed by the graph. We have something that's called a vertical asymptote. Okay. And a vertical asymptote is caused by the divide by 0 case in a rational function. Okay? So if I have a value that if I were to plug it into a function would result in dividing by 0, then we can't plug that in at all. It creates this thing called a vertical asymptote, or in other words, this line straight up and down that the function will always approach but never touch. Okay, just to show you a couple examples, right? We saw with the parent function that if I have 1 over x, your vertical asymptote would be at x equals 0, because you could not actually plug in 0 into that. It would give you an error. Consider the example of f of x is equal to 1 over x minus 5. Okay, having that negative 5 in the denominator. What value would now cause a divide by 0 case? Well, it would be at x equals 5. So 5 would be the location of your vertical asymptote in that particular case, right? Because you couldn't do, if you did 5 minus 5, you would get 0, and 1 divided by 0, you'd be like, I can't do that. This is bad. Your calculator's going to yell at you, right? So that's not good. And just to show you another one, what if I had f of x is equal to 1 over x plus 3, right? Something like that. Well, that's going to give you a vertical asymptote at x equals negative 3. Right, because negative 3 plus 3 is 0, and 1 divided by 0, again, is bad news. Okay, so that vertical asymptote always exists wherever the divide by 0 case happens to be. Okay, does that make sense to everybody? Hopefully, yes? Good. We also have the second type of asymptote is the one that goes this way. You might think it's called a horizontal asymptote. Sometimes you may hear it referred to as a horizontal asymptote, but we're going to actually use the vocabulary, which is a little more general and more proper vocabulary, of calling it an end behavior asymptote. Oh, and by the way, vertical asymptote is commonly abbreviated as VA. So if you see VA, just like I wrote it here, that stands for vertical asymptote. End behavior asymptote, not surprisingly, can be abbreviated as EBA, meaning end behavior asymptote. Okay? So the end behavior asymptote is caused by a value that the function can never equal. Okay? Just like how you saw here, and again, this can be abbreviated as EBA. All right? Just like how you saw that I can't plug in certain values, that's what creates vertical asymptotes, we get these things called end behavior asymptotes because we can't actually equal certain values either. All right? We can't actually equal certain values either. Here, there is no way that you could get the answer of 0 for in the y column. There's no x that you could plug in to make that occur, right? Does that make sense to everybody? I'll talk about how to find that end behavior asymptote in just a minute. It's a little trickier, but that's the general idea. That's the general idea. Does anyone have a question, comment, or concern about that? Feeling good about that, hopefully? Just blew my notes away. Okay, so let's actually, I know Luke has been asking a couple questions in the comments trying to be like, so how do you actually graph like a real deal example. I know you're giving me all this information about what an asymptote is, what a vertical asymptote, what an end behavior asymptote is, but how do you actually now like do it? Good question. Let me actually show you. All right, let me show you a real deal graphing example. Okay? All right. Suppose that you had this function. Ready? Something like f of x is equal to, let's do 1 divided by x minus 1 plus 3. Okay, real deal function that I could say, hey, go ahead and sketch a graph of that rational function. Well, as soon as you see that it's a rational function, number one, the thing that we're going to get into in a little bit, not today, but certainly trying to do any GCF or factoring, those will all come into play eventually, but we're not going to worry about that right now. The first thing I would do with this function is I would try to find my vertical asymptote if I want to sketch a graph of this. Okay? And again, your vertical asymptote is you're attempting to find the value for x that would result in dividing by 0. So hopefully at this point you can look at a function like that and be like, well, what value for x could I not plug in? Well, the value that I could not plug in is x is equal to 1. Because if you notice, if I tried to do that, I would get 1 minus 1 is 0, and then you would do 1 divided by 0, and the universe ends, right? We don't like that. It breaks the laws of math. Very, very bad. Okay? So that vertical asymptote being at x equals 1, I think that's a pretty quick and easy thing to be like, bam, x equals 1. If I gave you x plus 5 down there, you'd be like, bam, negative 5. If I gave you, I don't know, 2x minus 1, you'd be like, bam, 1/2. So that's the idea. To find your end behavior asymptote, it's a little trickier. So here's how you actually find your end behavior asymptote. Okay? To find your end behavior asymptote, what you want to do is you want to compare the degrees, ooh, we've seen that word before, of the numerator and denominator. Okay? Just a quick aside, hopefully you remember that that definition of degree refers to the highest exponent of a particular function to which a variable is raised, right? So if you have a function that has x squared in it and x squared is the highest exponent, there's nothing bigger than x squared that the variable is raised to, then your degree is 2. If you have x to the third and nothing is bigger than x to the third, you have then x to the third, 3 is your degree. Okay? So what I want to do is I want to compare the degree of the top and the bottom. Now, there are 3 cases. If you're comparing 2 things, there are 3 cases that can occur. Either the bottom is bigger, they're the same, or the top is bigger, right? So in all those 3 cases, it's important to know what to do. So let's start with, I don't know. I was like, where are my notes? My notes ended. I don't need them. I got it. I got it. All right. So 3 cases. All right. Case 1. If the degree of the denominator, meaning the degree of the bottom, is larger than the degree of the numerator. Okay, so if you look at your function and you notice, actually this happens to be the case here, but if you notice that the degree of your denominator is bigger than the degree of your numerator, then your end behavior asymptote is y equals 0 plus any vertical shift that you have on your function. And not surprisingly, just like we saw with radicals, a vertical shift is any number that gets added to the outside. And you saw with parabolas, right? That's the value that moves your function up and down, okay? The reason why I write 0 plus, because you might be like, well, why do I even say 0 plus? Why don't I just say the vertical shift? Is because the end behavior asymptote of this function by itself becomes 0, meaning that it's not going to ever hit 0. And then we just tack on any vertical shift that occurs. Okay? Is it necessary to write 0 plus? Of course not. But that's to show that the end behavior asymptote of this chunk right here is 0, and then we just add on the vertical shift. So if there is no vertical shift, then your end behavior asymptote is just 0. Okay? So that's a pretty simple one. Let's see. Any questions? No questions? Feeling good about that? Okay, cool. Case 2. I would say, well, what if they're the same? What if the degree of the denominator is equal to the degree of the numerator? Okay. What if they're the same degree? What if you look and they both have, like, this was, for example, 2x divided by x minus 1. In that case, both the numerator and the denominator would have the same degree, right? Because they would both have degree of 1. X to the first would be the biggest exponent on both the top and the bottom. Then, your end behavior asymptote is, let's put a colon here, y equals, and this seems like it's going to get crazy, but it's really not. Ready? It's the leading coefficient of the numerator divided by, like a fraction, the leading coefficient of the denominator, and then plus any vertical shift that you have. Okay? So essentially, your leading coefficient, or in other words, the number that's being multiplied to the variable that contains the highest exponent, right? Like, for example, if you have 2x, the leading coefficient would be 2. You take those coefficients, divide them by each other like a fraction, and then tack on any vertical shift that you have. Again, that seems like it would be tricky, but again, just consider my little example off to the side here that I just mentioned. If I had something like 2x divided by x minus 1, and then, oops, run out of room, then plus 3, say, for example. Well, they have the same degree. They're both degree 1. So you would just do leading coefficient divided by leading coefficient. That's 2 divided by 1, which is 2, plus 3. So your end behavior asymptote would be 5. Okay? So even though it seems intimidating when you're looking at that, you're like, oh my gosh, it's this big fraction. It's really not that scary. We just say, oh, it's the leading coefficient divided by leading coefficient, because it is going to increase at that rate, or it's going to approach that value. Not increase at that rate. It's going to approach that value, because the ratio at which both the top and bottom are increasing is going to come out to equal that. And then we tack on that vertical shift. Okie doke. And lastly, we have case 3. What if the degree of the denominator is smaller? Right? What if the top is bigger? Okay. So if we encounter a problem in which the top is bigger, then what happens is your end behavior asymptote becomes something that's called a slant asymptote, which is often abbreviated as SA. What that means is that your asymptote will no longer be just going perfectly horizontal at a value, but rather it'll be tilted either this way or this way, and your function will tilt along with that slant asymptote. We agreed, and by we, I mean the Algebra 2 CP teachers, agreed that this year, we usually do slant asymptotes, but this year, because of our limited time together, we are not going to be focusing or worrying about slant asymptotes. Okay, so you do not have to worry about slant asymptotes for our purposes in Algebra 2 CP. This year it will be honors only. Okay, so we do not have to worry about that case 3, just focusing on cases 1 and 2. Just because slant asymptotes do get a little tricky. It actually brings back an old skill of polynomial division, which I really like it for that reason, because it's a great review of polynomial division, but definitely with our limited time, I can certainly understand not having to focus on that. Okay. If anybody is curious and just wants to learn how to do slant asymptotes, then feel free to stop by my office hours and I'll be happy to show you. Okay? So that's how you go about finding your end behavior asymptote. I know that's a lot of notes, but let's actually get back to our example, and hopefully you'll see as we finish up in the next couple minutes that it's nice and quick. All right? Just in case I don't finish before our class officially ends, just to give you a couple of reminders to make sure you fill out that attendance form, I will post a couple of practice problems on graphing these types of functions on Classroom, so please make sure you get them done for next class. Okay? And I'll talk more about it later. But anyway, let's finish up this example. So this actual example, we have 1 over x minus 1 and then plus 3. Okay? We found our vertical asymptote of x equals 1, yes? To now find our end behavior asymptote, I would look at these three cases. The degree of the denominator here, if you notice, is 1 because this is x to the first power, right? So it has a degree of 1. The degree of the numerator, if you notice, is 0 because there aren't any x's at all. There are no x's. So therefore, it would satisfy case 1, where the degree of the denominator, which is degree 1, is larger than the degree of the numerator, which is degree 0. Okay? So therefore, our end behavior asymptote in our example is going to be 0 plus the vertical shift. The vertical shift is 3. So your end behavior asymptote is y is 3. Okay? Now we can go ahead and sketch a graph quickly. So just to show you. I'm going to draw in our end behavior asymptote at x equals 1. That's this vertical line that goes right through the x coordinate of 1 on the x-axis. We have our end behavior asymptote of y is equal to 3. Right here. It just goes horizontally like this, right through the y-axis value of 3. And now what I'm going to do in order to sketch my graph, so now I have like a nice little starting point. This is going to be the center of these two curves, whether it's going to be looking like this or looking like this. I really don't know if it's going to be either corner. So what we can do now is test some points. So what we're going to do is we're going to test points. Okay. In order to test some points, what I'm going to do is I'm going to create a little table of values. And I'm just going to very quickly plug in 2 values to the left of this little cross section here. So I'm just going to go 2 values to the left and 2 values to the right, just so I can get a nice picture of what my function looks like. There's no mathematical rule or law that says we have to go 2 this way and 2 this way. But just like with parabolas, I think it's a great, I think it's like that Goldilocks zone, the perfect number that actually gives you a nice picture of the graph. I don't think 1 point is enough to get a good picture. And I think by the time you get 3, it's like excessive. Then you clearly see what it looks like. So 2, I think, is a good measure. So since my x coordinate right here is 1, we're going to plug in -1 and 0 from the left. And from the right, we're going to plug in 2 and 3. Do you see that? Because that's going to be 2 points, 2 x values to the left and 2 x values to the right of this little cross section here. So now we just take these values, plug them in, and see what we get for our answers. So if I plug in -1, you're going to get -1 minus 1 is -2. 1 divided by -2 is -1/2 or -0.5. Plus 3 is going to be 2.5. So I have a point at -1, comma 2.5. Here's 2.5 right about there. Okay. I plug in 0. 0 minus 1 is -1. 1 divided by -1 is -1. Plus 3 is 2. So I have a point at 0, comma 2. And you should see those 2 points being there is indicative of the fact that the function will be approaching the asymptotes but not touching them. So now I'm going to draw in my curve to look just like the ones from before, and that's going to be a curve that approaches but never touches the asymptotes. I knew to draw it that way because these asymptotes served as guidelines for me for how to draw my function, right? I draw it to approach but never touch the asymptotes. Okay. Now I just do the same on the opposite side. So I go ahead and plug in 2. 2 minus 1 is 1. 1 divided by 1 is 1. Plus 3 is 4, so I have a point at 2, comma 4. 1, 2, 3, 4 right here. I plug in 3. 3 minus 1 is 2. 1 divided by 2 is 1/2. Plus 3 is 3.5. So I got a point right here. If you notice, this should look pretty symmetrical. Not pretty symmetrical, it should look exactly symmetrical with those points over there. So I can again draw in a curve that goes through these 2 points and approaches but does not touch the asymptotes. And keep in mind that these are smooth curves and not corners. They're not right angles. They're nice smooth curves. Okay? Does anyone have a question about how that's done? Feeling good about that? Hopefully that makes sense. Yes? So, just to recap, a rational function, I know I went over time, and I appreciate everybody sticking around. This recording is going to be going up on YouTube just like all the others, so you can feel free to watch back if you need to. Okay? A rational function, just to recap, is any function that has a variable in its denominator. Okay? Having variables in the denominator, though, causes these things called asymptotes. You have a vertical asymptote, goes up and down, and behavior asymptote goes left and right. Okay? In order to actually graph a function, what I actually do is I first find the vertical asymptote, find the value for x resulting in dividing by 0, number 1. Number 2, find the end behavior asymptote by adhering to these 3 cases. Okay, it's important that you know those cases. In this particular example, our end behavior asymptote satisfies case 1, so it's y equals 3. Once you draw your asymptotes on the coordinate plane, I now just go ahead and plug in 2x coordinates to the left and 2x coordinates to the right, just like I did here, just so I can plug them into my function and get a nice pretty picture of what's going on. Remember that when you draw your curves, they should be approaching but not touching the asymptotes. Okay? So for next class, I am going to give you a couple problems to try on your own, probably like 3 or 4, maybe 5, I don't know, 3 to 5 problems. That's not going to be crazy. Just some basic problems like this that I'd like you to get a little hands-on practice with first. I'll be happy to go over them again for another class. I also want to talk a little bit about domain and range of these functions next time. And then we'll do just some more practice problems, okay? So I'll talk a lot more about what quarter 4 grading is going to look like as well next class, because I know there's a lot of questions on that. How many assignments we have, what are the assignments going to look like? I'll be sure to address that next class. But again, I'll just throw up a couple practice problems for you for the weekend for you to work on, okay? We do not see each other again until next Tuesday, so you should have plenty of time to try these on your own. And again, refer back to this example if you need to. Thank you for your attention and focus today. Again, sorry for going way over the time limit, but I really appreciate you sticking around. That was information I really wanted to get to you. So thank you again. I hope you have a fantastic rest of your Thursday afternoon, and I will see you next Tuesday. Have a great weekend. All right? Stay safe, stay healthy, okay? Thank you.